When we gaze upon the universe, it's hard to believe that everything we see, planets, stars, galaxies, and the intricate life around us, just happened by chance. Everywhere we observe the universe, it follows the same rules. It has consistent fundamental properties containing the same building blocks, and these building blocks naturally come together in ways that not only allow the creation of everything we know but almost make it seem like destiny. Our universe appears finely tuned for this, but was it always bound to be this way? Why are we here, and why does the universe seem tailor-made for us? This is often referred to as the Goldilocks paradox. Imagine if the force that holds atomic nuclei together were just a bit stronger. Our sun would have burned out in an instant, and life on Earth wouldn't exist. Conversely, if the weak nuclear force were a little weaker, the essential elements of our world wouldn't exist, and neither would we. If gravity were slightly weaker, it couldn't have ignited the sun's nuclear reactions to create sunlight. If it were stronger, the sun would have exhausted its fuel long ago. These are just a few examples of how the laws of physics appear finely tuned. Many fundamental aspects of nature, like the strengths of forces and the masses of particles, seem perfectly adjusted for life to exist. It's as though the universe was designed for us. Do all of these mean that we are special, or are we just lucky? What does it mean for something to be finely tuned? It may not be as easy as it sounds, but let me explain it like this. I want you to pick a number between 1 and 1 million, and you can choose any number within that range. Go ahead and select a number between 1 and 1 million. I'll do the same. Now, before we reveal our numbers to each other, here's what we'll do. Once we reveal our numbers, we'll subtract my number from yours. Then we'll compare the result with what we'd expect, and this will help us understand the idea of fine-tuning. My number was 659,349. When you subtract it from your number, whatever it is, here's what we expect. There's a better chance of getting a negative number, but about a 34% chance of getting a positive one. It's extremely unlikely that the result will have 3 digits or fewer. If our numbers match exactly, it's very likely there's a specific reason behind it, like psychic powers, or you watched the video before I published it. When the difference between these numbers is significantly smaller compared to the original numbers themselves, that's an example of fine-tuning. It might seem like a rare coincidence, but your first guess would be that there's a deeper reason behind it. Think of the universe as a giant recipe. Imagine you're baking a cake, and there are many ingredients you can choose from. You need to pick the right ingredients and use the right amounts to make the perfect cake. Now, if you change just one ingredient a little too much or use the wrong amount, your cake won't turn out right. It might not even be edible. In a similar way, the universe seems like it's been carefully cooked with just the right ingredients and quantities to allow life to exist. If any of these cosmic ingredients were different by even a little bit, life as we know it might not be possible. This fine-tuning of the universe suggests that there might be something more than chance at play, as if the universe was a recipe just for us. If we come back to the expanding universe, that's the situation we find ourselves in. The universe appears to be enormously fine-tuned. On the one hand, we have the expansion rate that the universe had initially, close to the Big Bang. On the other hand, we have the sum total of all the forms of matter and energy that existed at that early time, including radiation, neutrinos, normal matter, dark matter, antimatter, and dark energy. Einstein's general theory of relativity helps us understand how the universe's expansion rate and the types of energy it contains are connected. By knowing what the universe is made of and how fast it initially expands, we can predict how it will change over time, including what will ultimately happen to it. In our universe, there's a delicate balance between the amount of matter and energy it contains and how fast it's expanding. If there's too much matter and energy, the universe would collapse quickly. If there's too little, it would expand into emptiness before even forming atoms. Surprisingly, our universe has neither collapsed nor expanded aimlessly even after 13.8 billion years. If we rewind the clock to a tiny fraction of a second after the Big Bang, we discover that this balance needs to be incredibly precise. The initial expansion rate and the sum total of all types of matter and energy in the universe must match to an astonishing degree, more than 20 decimal places. It's like guessing the same 1 to 1 million number as me 3 times in a row and then correctly predicting the outcome of 16 coin flips immediately after. The chances of this happening by random chance, considering all the possibilities, are extremely tiny. It's possible that the universe was naturally born with this perfect balance between its contents and initial expansion rate. It's possible that it has always been this way. However, in science, when we encounter a seemingly unexplained coincidence, it's not enough to simply assume it's due to initial conditions. From a scientific perspective, it's better to try to find a reason for why this coincidence might exist. One possible explanation is to suggest that there are countless different outcomes and universes out there. We just happen to exist in a universe where our existence is possible, which is why everything seems perfectly tuned for us. It might be true that the universe could have been anyway, and we happen to live in one where things are as they are. However, relying on this idea, called the anthropic principle, doesn't provide us with a scientific solution. It's like saying we've given up on finding a real scientific answer to the puzzle. We'll get back to this anthropic principle later in the video. However, a solid scientific argument should do 2 key things. It should explain how these seemingly finely tuned conditions come about, and it should make specific testable predictions that are different from what we'd expect without that explanation. The second point is what sets a scientific argument apart from a non-scientific one. If you can only rely on the starting conditions of a problem, you won't have a way to test your scenario further. While other universes might exist, if we can't observe them and determine if they share the same initial conditions as ours, it lacks scientific value. On the other hand, if a prior phase of the universe created these initial conditions while also making additional testable predictions, that would be of great scientific significance. When we consider the energy balance of the universe, where the expansion rate seems to align perfectly with the total energy, a theory like cosmic inflation is a strong contender. Inflation could stretch the universe flat, creating the right energy balance for the expansion rate. When inflation eventually stopped, it set up the initial conditions for the Big Bang. Moreover, inflation also makes extra predictions that we can test through experiments or observations, providing the scientific rigor we need. Many fundamental constants have values that seem just right for life to exist. In 2000, astronomer Royal Martin Rees boiled them down to 6 in his book, Just 6 Numbers. The first number, denoted as n, represents the ratio of 2 fundamental forces, the relative strength of the electrostatic to the gravitational force between 2 protons. The value is 10 to the power of 36. N determines the smallest size a star can be, similar to our Sun. It tells us when an object's gravity can overcome the repulsive electromagnetic forces that push atomic nuclei apart, allowing nuclear fusion to happen. If N were larger, it wouldn't have a significant impact. But if it were smaller, stars would be smaller too and burn their fuel faster, making it less likely for life to evolve. Next is the second number, epsilon, denoted as this symbol. It represents the proportion of a hydrogen atom's mass that's released as energy when it's fused into helium inside a star. The value is 0.007. The fusion of hydrogen into helium is crucial for creating heavier elements and enabling complex chemistry, which is essential for life. If the value of epsilon were slightly smaller, nuclear fusion wouldn't be possible, and the universe would only consist of hydrogen. If it were a bit larger, all the universe's hydrogen would have been used up during the Big Bang, and there wouldn't be any stars. Now let's consider the third number, omega, denoted as this symbol. It represents the ratio of the actual density of matter in the universe to a theoretical critical density that, if exceeded, would cause the universe to collapse under its gravity. The value is approximately 0.3. Omega plays a role in determining how fast the universe expands. If it were higher, the universe would have collapsed a long time ago. On the other hand, if it were lower, the expansion would have been too rapid, preventing the formation of stars and galaxies. Moving on to the fourth number called lambda, which represents the cosmological constant. This constant is related to the energy that comes from tiny fluctuations in the vacuum of space. The value is approximately 0.68. Lambda is considered a leading candidate for the mysterious force driving the universe's accelerated expansion. If it were smaller, that wouldn't be an issue. However, if it were significantly larger, the universe would have expanded so rapidly that stars and galaxies wouldn't have had enough time to form. Now let's look at the fifth number, denoted as Q. It represents the amount of energy needed to break apart a galactic supercluster compared to the total energy stored in all of its matter. The value is approximately 10 to the power of -5. Q is like a measure of the size of small fluctuations in the early universe that eventually grew into stars and galaxies. If it were smaller, the universe would be motionless and without structure. If it were larger, the universe would be dominated by black holes by now. In either case, it wouldn't be suitable for supporting life. The last number, denoted as D, represents the number of spatial dimensions we live in. The value is 3. Our universe has 3 spatial dimensions, and this is just right for stable planetary orbits and the possibility of life. If we had 4 spatial dimensions, planetary orbits would be unstable, and with only 2, life as we know it would be impossible. These 6 numbers collectively describe the fine-tuned conditions necessary for the universe as we know it to exist and support life. It's as if the universe has been precisely calibrated to allow the formation of galaxies, stars, and planets, and the emergence of life itself. Even slight changes in these numbers would have drastic consequences. Stars might not ignite, galaxies might not form, or the universe could have quickly collapsed or expanded beyond recognition. The fact that these values appear just right for our existence raises profound questions about the nature of our universe and whether it was finely crafted for life or the result of some deeper physical principles we are yet to uncover. Spacetime expands or contracts, curving based on the matter and energy contained within it. Particles attract, repel, or bind together based on the conditions under which they interact. Some systems will be stable, some will decay. The scientific process is very powerful and does a remarkable job at telling us how these things happen. But it doesn't always explain why they happen or if they were bound to happen that way. Sometimes we need a guiding principle to help us understand more about the universe. Having a guide can be really useful when we're trying to learn more about certain problems. For a long time, we've known that the universe has many different types of elements, atoms with varying numbers of protons in their cores. In fact, there are at least 59 different elements inside your body alone. But for a while, we didn't fully understand how these elements were created. However, one thing has always been clear: we exist to explore and observe the universe. This straightforward fact holds significant meaning. It suggests that our universe has properties that allow intelligent observers like us to evolve within it. Think of it this way: if the universe had properties that made intelligent life impossible, we wouldn't be here to discuss it. The fact that we exist to observe the universe indicates that it's structured in a way that allows us to exist. This idea is called the anthropic principle, and it has valuable lessons to teach us. The idea of the anthropic principle was first put forward by Brandon Carter, an Australian physicist and mathematician, in a paper he presented in 1973. In this paper, Carter suggested that the seeming fine-tuning of the universe's physical constants and conditions for the emergence of intelligent life could be understood by the fact that we can only observe a universe that allows our existence. The concept of the anthropic principle was initially talked about by physicist Robert Dicke in the late 1950s. Dicke was curious about why the laws of physics have the specific properties they do, and he proposed that it might be because these laws allow for the existence of life. There are 2 main types of the anthropic principle: the weak anthropic principle and the strong anthropic principle. The weak anthropic principle says that the universe has to allow for the existence of intelligent observers because otherwise, we wouldn't be here to observe it. In simpler terms, the universe's conditions have to make intelligent life possible, or else we wouldn't be around to see it. The strong anthropic principle, on the other hand, goes further and suggests that the universe is finely tuned specifically for the existence of intelligent life. This version of the anthropic principle implies that the universe was designed or created with the purpose of producing intelligent life. Back in the early 1950s, scientists were grappling with a puzzle. They understood that stars, including our Sun, generated energy through nuclear fusion, specifically by turning hydrogen into helium. However, this process only explained the creation of the two lightest elements in the universe. The problem was that there seemed to be no way to make heavier elements. When you tried to combine hydrogen and helium to create something heavier, the math didn't add up. It turned out there was no stable combination with atomic mass of 5, and other attempts failed too quickly. Then, in 1952, scientist Fred Hoyle used the anthropic principle to reason that there had to be a process for making heavier elements. He suggested that a third helium atom could somehow interact with the unstable beryllium-8 to create carbon-12. However, there was a significant problem: the masses didn't